In this short video, let us see the voltage divider rule for the capacitors. So this voltage divider rule for the capacitors is little different from the voltage divider rule for the resistors and the inductors. As you know, in case of the resistors, if the two resistors are connected in the series connection, then the voltage across the specific resistor R2 can be given by the following expression. That is the value of the resistor R2 itself divided by the equivalent resistance of all the resistors which are connected in the series connection, and then it will get multiplied by the voltage V. And the same is the case for the inductors. So if the two inductors are connected in the series connection and the voltage across them is equal to V volt, then the voltage across the specific inductor L2 can be given by the following expression. That is inductance L2 itself divided by the total inductance of the series connection times V volt. But if you see the voltage divider rule for the capacitors, then it is different. That means if two capacitors are connected in the series connection and the V voltage is applied across it, then the voltage across the capacitor C2 can be given as this C1 divided by this C1 plus C2 times V volt. Similarly, if you want to find the voltage across the capacitor C1 at the specific time, then it can be given as this C2 divided by this C1 plus C2 times V volt. So in the first case, although we are finding the voltage across the capacitor C2, but in the numerator, we will have the capacitance of the opposite capacitor. So let us see why is it so, and let us derive the expression for the same. So here, since the two capacitors are connected in the series connection, so the same current will flow through both the capacitors. So at any given time, if we see the charge across any of the two capacitors, then it will be the same. So we can say that the charge across the capacitor C1 is same as the charge across the capacitor C2, and that is same as the net charge Q that is supplied by the source. That means whenever the capacitors are connected in the series connection, then the charge across each capacitor will remain same. But here, depending on the capacitance value, the voltage across each capacitor will be different, and it can be given by following expression, that is Q is equal to CV. So we can say that the net charge that is supplied by the source is equal to C equivalent times V, where the C equivalent is the equivalent capacitance of this series connection. So here, since the two capacitors are connected in the series connection, so their equivalent capacitance is equal to C1 parallel C2, or we can say that is equal to C1 times C2 divided by C1 plus C2 times V. That means the net charge that is supplied by the source at any given time is equal to C1 times C2 divided by C1 plus C2 times V. And as we know, the charge across the capacitor C1 and C2 will also be the same. So here, the charge across the capacitor C1 or this Q1 is equal to C1 times V1. And similarly, this charge across the capacitor C2 can be given as C2 times V2. So in the expression of the charge Q1, let us put the value of the Q. That means now, this charge Q is equal to C1 times C2 divided by C1 plus C2 times V, that is equal to C1 times V1. So here, this C1 will get cancelled out on the both sides. And we can say that this voltage V1 is equal to C2 divided by this C1 plus C2 times V. Similarly, we can also find the voltage across the capacitor C2. So once again, in the expression of the charge Q2, let us put the value of the Q. So we can say that this Q2 is equal to C1 times C2 divided by C1 plus C2 times V, and that will be equal to C2 times V2. So once again on the both sides, this C2 will get cancelled out, and we will have this voltage V2 that is equal to C1 divided by this C1 plus C2 times V. So in this way, when the two capacitors are connected in the series connection, then this is the voltage divider rule for the capacitors. Similarly, now let us see the voltage divider rule when more than two capacitors are connected in the series connection. So here, three capacitors C1, C2 and C3 are connected in the series connection. So in this case, the voltage across the capacitor C3 can be given by the following expression. So in this case, in the numerator, we will have the equivalent capacitance of the other capacitors other than C3. So here, since the C1 and C2 are connected in the series connection, so their equivalent capacitance will be equal to C1 parallel C2. So here, when we are saying C1 parallel C2, then it is basically a mathematical operation. But physically, these two capacitors are connected in the series connection. That means in the numerator, we will have the C1 parallel C2, and in the denominator, we will have the C1 parallel C2 plus C3, and this entire term will get multiplied by the voltage V. Similarly, if we see the voltage across the capacitor C1, then it can be given as the C2 parallel C3 divided by the C2 parallel C3 plus C1 times V volt. So now let us see how we got this expression. So once again, here since all the capacitors are connected in the series connection, so the same current will flow through all the capacitors, and hence the charge across all the capacitors will also remain same. So we can say that over here this Q1 is same as the Q2, and that is also same as the Q3, and that will be equal to Q, that is the net charge that is supplied by the source at the any given time. But once again, here depending on the capacitance value, the distribution of the voltage across each capacitor will be different, and it can be found using this expression, that is Q is equal to CV. So here the net charge that is supplied by the source can be given as the C equivalent times V, where here the C equivalent is the series connection of the three capacitors, and that is equal to C1 parallel C2 parallel C3. So once again, here this parallel is the mathematical operation between the capacitors, but in reality they are connected in the series connection. So we can say that this Q is equal to C1 parallel C2 parallel C3 times V, or further we can say that this Q is equal to this C1 times C2 divided by C1 plus C2 parallel C3, and of course it will get multiplied by the V volt. So if we further simplify it, then it can be written like this. So in the numerator, we will have the C1 C2 divided by C1 plus C2 times C3, and in the denominator, we will have the C1 C2 divided by C1 plus C2 plus C3, and once again it will get multiplied by the V volt. So if we further simplify it, then it can be written as the C1 times C2 times C3 divided by the C1 C2 plus C2 C3 plus C1 C3 times V volt. So that is the net charge that is supplied by the source. And if we see the charge across the Q1, Q2 and Q3, then it will also be the same. So if we see the charge across the capacitor C3, then that is equal to C3 times V3. And this charge will be same as the Q. So here, now let us put the value of the Q. So further we can write it as the C1 times C2 times C3 divided by the C1 C2 plus C2 C3 plus C1 C3 times V, that is equal to C3 times V3. So here the C3 will get cancelled out on the both sides, and we will have this voltage V3, that is equal to C1 C2 divided by C1 C2 plus C2 C3 plus C1 C3 times V volt. So in the denominator, if we take the C3 outside, then it can be written like this. And further, if we divide both numerator and the denominator by the C1 plus C2, then this voltage V3 is equal to C1 C2 divided by C1 plus C2, and in the denominator we will have the C1 C2 divided by C1 plus C2 plus C3. So that is equal to C1 parallel C2 divided by the C1 parallel C2 plus C3 times V volt, and that is the voltage across the capacitor C3. And similarly, we can also find the voltage across the capacitor C1. So that is the voltage divider rule for the capacitors. And in this way, when more than two capacitors are connected in the series connection, then this is how we can find the voltage across the specific capacitor.